next topic is PIN, but this time shot noise. So I said that PIN creates thermal noise, but it also creates something called shot noise, and which is a little more interesting, actually, than thermal noise. The shot noise has its origin in the fact that the photons arrive with Poisson statistics. And time allowing, I'll get into a little bit of the discussion of this origin on Thursday, although realistically I don't think I'll have much time. It's a white process. So shot noise is a white process. And although if we speak rigorously, it's a Poisson process, in the regimes of operation it is well approximated as Gaussian, again in most telecom systems. So it's a white noise process, well modeled as Gaussian. So far it sounds very similar to the thermal noise, but there's a very important distinction in one way that it's different, and in one way that often distinguishes between radio frequency digital communication systems and optical communication systems is that the noise varies with the input power. The noise power varies with input signal power. So it's knowing that the origin of shot noise is from the Poisson arrival statistics sort of makes sense. The stronger the power of the arrival, the stronger the noise is. So remember, thermal noise is not like that. No matter how strong the signal is, thermal noise is a fundamental limit, not related to the signal strength, whereas shot noise is more severe for larger signals. Now, of course, we're talking about digital communication systems, and of course in digital communications there is the logical 0 and the logical 1, which means that the instantaneous power will be different depending on which data is sent, which means the shot noise power will be different depending on whether a logical 0 is transmitted or a logical 1. For now, let's just consider a continuous wave signal, what the equations are for the shot noise. So we'll think of it in terms of instantaneous power to just keep these ideas clear in our mind. Instantaneous power. So the power spectral density of shot noise is equal to the electron charge Q times the responsivity of the photodiode times the input signal power. So this is the electron charge, responsivity, which is given by, if you want, the efficiency of the PIN times the electron charge divided by Boltzmann's constant and the frequency. And this is the signal power. So right away we can see that what we should be talking about are two different power spectral densities. One is for a logical 0, which would be QRD times the power in a logical 0, and the shot noise for a logical 1, QRD P1. In a perfect optical communication system, of course, P0, there would be, well, I'm going to talk today exclusively about on-off keying. Which is also known as intensity modulation with direct detection. So on-off keying would be the term used for all digital communications. When in particular we use on-off keying in an optical communications system, we typically refer to it as IMDD. So assuming that this is the modulation type we're using, in theory the power on a logical 0 should be 0. But in fact, the optical components that we use lead to a finite extinction ratio so that the power is not completely 0 during the transmission. So whatever that power is, small though it is, there will be some shot noise induced by it. Again, the power spectral density of the shot noise is just a flat over all frequencies, or maybe we'll say the bandwidth of the of the PIM. And so the same as we saw before, the sampled noise, shot noise, has variance. So sampled noise variance is NSN times the noise equivalent bandwidth.